Here's going to be the lab for the refraction of light in a glass. And we're going to be writing all these values in, and what I want you to do is just sort of follow along, because we're going to do very similar to what we did in lecture, where we have a piece of glass and we have a laser light, and I'm going to be using a ruler, and we can measure the incoming angle and we can measure the outgoing angle, and we know the index of refraction for air, and that will enable us to calculate the index of refraction for this material right here. So that's what we're going to be doing in the lab, and we'll get to these questions a little bit later. So you do not have to draw all of this. All that you'll have to do is to follow along and to write all the details in. So I am going to start with my piece of glass in the middle, and I'm going to draw it more towards the bottom right here. And I'm going to trace the outline. So a lot of this is just going to be watching and following along. Now, the data sheet says we want incident angles of coming in at 30 and 40. So we're going to do this 2 different times. And I'm going to be picking a point that the light's going to be coming in. And I need to draw my normal. So there's my first normal. And what I need to do is I need to measure from this point, I need to measure 30 degrees from the normal. Okay, so I'm going to have this like this. And you can see the protractor is going in 360 degrees. And this is going to be going off at an angle of 30 degrees. So I'm going to be marking that. That's going to be my incoming angle right there. That's going to be my 30. And I'm going to also come in at 40 as well. Okay, so I'm going to be coming in at that angle. So these are my angles of incidence. So I'm going to connect that point there and connect this right there. So from here to here, this is the angle of incidence, the incoming angle, and that's going to be 30 degrees. And the angle from here to here is going to be the 40-degree angle of incidence. We're going to measure how much the angle is refracted, and then we will also see and calculate the index of refraction based upon the refracted angles. So I'm going to go ahead and dim the light down, and I'm now going to take the laser light. I'm setting it on the line, and I am putting it towards the this tile, and I want to see where is it exiting. So it's going to be exiting right about here and going to here. Now I'm also going to come in at a 40-degree angle. And try to do this again just to be sure. That looks about right. Okay, so now what I'm going to do is I'm going to turn the lights back on, and we're now going to draw these. So at a 30-degree angle, the refraction was there, and at a 40-degree angle, the refraction was there. This then flared outward, and then this also flared outward as well. Okay, so I'm going to draw the 2 normals for this one, and I'm going to draw the normal for this one. So what I want to calculate, or what I want to figure out, is what is the, and they use a lowercase r, what is the angle of refraction right here? So that's what we're going to try to find, is the angle of refraction. We're not going to worry about this. We're not going to worry about this. We just want to know what is the refracted angle and what is the second refracted angle as well. This is the one that's coming out of the glass to here. So I'm going to use this, this protractor to the very best of my abilities and to calculate what is the angle of refraction. So you guys can see this protractor, and we are always taking it from the angle of the normal. So here's the normal. I'm measuring it from the normal and not from the surface. So from here to the 30-degree angle, and I need to use the ruler for this, and we're going to see what it points to. It might be easier to do it from this way. You're going to line it up here. And what we see is it goes 10 degrees, 20 degrees, and it looks like that it's pointing towards 21 degrees. So I'm going to be putting in 21 degrees. Now what I'm going to do is I'm going to measure the angle of refraction for the larger angle. And I'm going to follow this line, and it would point towards 10, 20, 25, 26 degrees. So it's a larger angle, so it's a larger angle of refraction as well. And I'm also going to be measuring the, from this point, what is the outgoing angle. And it came in at 30. It should leave at 30. And if you follow this, it looks like it came out at 32 degrees. But ideally, it should have come out at 30 degrees to match the incoming at 30 degrees. And this should be 40 degrees. And lining it up, it looks like it's about 35. It looks like it's about 38 degrees. So it's close to the original 45. So now what we need to do, we've done all of our measurements. Now we actually need to do the calculations. So this is what you will need to do on your lab. So we're using Snell's law. And Snell's law is going to be the index of refraction times the sine of the incident angle is going to be equal to the index of refraction times the sine of the refracted angle. So we're going to use that for both of them. We're trying to find the index of refraction of this material for both substances. So that's what we're trying to find. So we're going to divide both sides by sine of theta r, divide by sine of theta r. And this is really interesting. If you remember the incident index of refraction, this is coming from air. So coming from air is equal to 1.00. So that actually cancels out, because if you multiply anything by 1, it's not going to change the value. So take a look at what this really means. The index of refraction is the ratio of the sine of the incoming angle to the sine of the refracted angle. Okay, and index of refractions will always be greater than or equal to 1. So let's go ahead and calculate this. So I have the sine of my incoming angle, which is at 30 degrees. So I'm going to do sine of 30. You could probably turn the lights on too. So we have the sine of 30. Divided by the sine of the refracted angle, which is 21, divided by the sine of 21. Okay, this gives me an index of refraction of 1.32. 395, 1.40. Okay, going to do the same thing here. The index of refraction is going to be the sign of the incoming, which is, oh, I did 40 instead of 45. Okay, so my bad, we did 40. That's really important. So we have the sine of 40 divided by the sine of the refracted angle of 38. No, I'm sorry, of 26. And that gives us 1.47. So here's the question. These should have been the same number based upon our values and our angles. They're a little bit off. Is there good agreement between the two values of the index refraction of the plate of glass? So last year we got around 1.40. So this value is closer. So the values are close based upon our measurements. According to the diagram, are light rays refracted away or toward the normal as they pass at an angle from an optically less dense, okay, less dense means that, for example, it's traveling from air into an optically more dense. This is going into the glass. So this is going back to the previous question, or from lecture. When I have the angle of 30 degrees coming in, which direction we would expect it to continue on its path to go like this, but it actually bends inward toward the normal. So is the light refracted away or toward the normal? Okay, this is going to be toward the normal. So going from air into glass, the light bends toward the normal. Okay, now if you see here, here's the 30 coming into the glass. We would expect it to continue on its path like this, but it doesn't. It actually bends outward away toward the normal. So when it's going from optically more dense in this case again is the glass. When it's going from the glass to less dense, such as air, the light is going to bend away from that normal. So compare the incident angle and the second refracted angle. Is the measure of the refracted angle what you would expect? Okay, now we're comparing 30 and 32 and 40 and 30, 38. So those values are also close as well. So we would expect the incident angle to be equal to, and I'm going to use what we use in, it's going to be the R2. In this case, it's the R prime for this lab, R prime. Just following lecture notes. We would expect this to be true. So the speed of light in air is so close to the speed of light in a vacuum, you can consider them to be equal. Use the results to determine the approximate speed of light as it travels through glass. So here's the formula for the index of refraction. The index of refraction is going to be equal to the speed of light divided by the velocity. So whatever substance it is, so it's going to be the glass. We're trying to solve for the speed of light going through the glass. Okay, so what happens is we can rearrange this, and when we rearrange it, it will be looking like this. So the velocity is going to be equal to the speed of light divided by the index of refraction. This makes sense because if you're in a vacuum, the speed of light divided by 1 would be the speed of light. So the speed of light is 3.00 times 10 to the 8th meters per second. divided by, in our index of refraction, let's kind of average these together because it's probably somewhere in between there, plus 1.47 divided by 2. The average is going to be equal to 1.435. And if we plug that value into here, 1.4, we'll just say 3 digits, 1.44. Taking the speed of light, 3 times 10 to the 8th divided by 1.44. So the speed of light is going to be equal to 2.08 times 10 to the 8th meters per second. Okay, by what percentage of the speed of light is it traveling in a vacuum faster than the speed of light? This is, so if you just take if you take the speed of light, 300 divided by 208, you actually get 1.44. This means that the index of refraction is also an indication. The 1.44, this is the speed of light. So the speed of light is 1.44 times faster in the vacuum or in the air. So the index of refraction, you can also say it's 1.44 times slower in the material as well. So the index of refraction is very valuable. It tells us how optically dense it is. It tells us how much it's going to bend toward or away from the normal. It can also tell the velocity of light in that substance as well, and how fast it's going compared to the speed of light in a vacuum. That's it.